Welcome back. In this video, we're going to be talking about the classical dynamics of a spinning particle in a magnetic field and about motivating Schrödinger's equation. So before we get to that, broadly speaking, you could say that all of physics is really just two questions. What are physical states? And how do they evolve in time? So far in this video series on quantum spin, I've talked a lot about what the physical states are for quantum spin. They're just two-dimensional complex vectors. But I haven't yet said how they evolve in time. So the question we now want to address is, what makes a quantum spin state change? And the answer to that question is a magnetic field. So throughout this video, here's the sort of general setup you should be picturing in your head. There should be some sort of magnetic field in space, right? So this is a B field, right? A magnetic field. And this could be placed there, say, by an experimenter on purpose. It doesn't really matter how it got there, just some external magnetic field. Then in this magnetic field, there is a point-like electron which has a spin state of psi. Furthermore, there is no external electric field. So the external electric field is 0. I mean, there will be some electric field because an electron is there, but I mean, there's no other electric field, right? So no external electric field. And because of this, the electron won't move around. It'll just stay stationary. So throughout this video, I'm not going to be dealing with how electrons move. I'm just going to assume it's just planted at one location, and I'm only interested in discussing how the spin state changes. I'm not going to be discussing the motion of an electron. I'm planning on discussing this in a future video, but I'm not going to talk about it now. Now, before we talk about quantum mechanics, we're going to start by building intuition by just looking at what happens classically. And we'll see that what happens in quantum mechanics isn't actually too different from what happens classically. So we're going to start by building some intuition. So classical dynamics. So here we're going to be pretending that the electron is a charged spinning sphere, like a charged spinning baseball with a constant charge density throughout its volume. So we're going to say it's spinning with some angular frequency of omega sub spin, right? And by angular frequency, I mean that if you say that omega sub spin, which is just the magnitude of this vector, omega sub spin, then the period of this rotation, which is usually called t, is equal to 2 pi over omega. So that's what I mean by the angular frequency. And the idea is it's spinning like this, as per the right-hand rule. So the next thing I'm going to introduce is an external magnetic field, B, which just for simplicity, I'm going to have pointing at a right angle from this axis of spin. And this magnetic field is constant throughout all of space, but I'm only going to draw this one vector. So the next thing I want to look at is what forces the magnetic field exerts at different parts of the electron. So let's start with this leftmost point here. So this leftmost point of the spinning sphere has a velocity vector coming out of the screen. and you denote a vector coming out of the screen by this dot with a circle around it. So that's the velocity at that point. Likewise, the velocity at the rightmost part of the spinning sphere is going into the screen. And you denote that with a circle with an x in it. And that's the velocity at that point. And this is just because, you know, the electron is spinning like that. Now, in order to figure out what the force is on different parts of the spinning sphere, we need to remember what the Lorentz force law is. So the Lorentz force law. And that is that the force that a magnetic field makes on a moving charge is equal to Q, where this is the charge, times the velocity v at which the charge is moving. And then we have the cross product. And then we have the magnetic field. So now let's look at this part of the sphere right here, this point of the sphere. What is V cross B? So I'm now doing the right-hand rule to figure out what V cross B is. Okay, are you doing it too? So where's V cross B? It is pointed this way. That is V cross B. But remember that the electron is actually negatively charged. So the charge of this little part of the sphere right here is actually negative. So the force on that part of the sphere will be pointed in the other direction. So this is the force, this is the direction of the force exerted at this part of the sphere. And then on this part of the sphere on the right, the force is going in this direction. So the force is going up on the left half of the sphere and down on the right half of the sphere. So what can we see here? We can see that the force on one half of the sphere is equal and opposite to the force on the other half of the sphere. So that means that overall there is no net force on this sphere. So that means that the center of mass will not move. But, and this is the important part, but there is a net torque on the sphere. So let's verify this. So remember that the equation for torque is that torque is equal to the position of whatever it is you're looking at. So here I'm going to denote position with R. So position cross force. Okay, so let's look at the torque at this part of the sphere and the torque at this part of the sphere. All right, so here's the center of the sphere, and here's the position vector for this left part of the sphere and for this right part of the sphere. And okay, I'm now going to figure out the direction of the torque on this left part of the sphere. So I'm taking out my right hand. Okay, torque is R cross F. So I'm doing the right hand rule. R cross F. So what direction is the torque pointing? Well, I am getting, according to my thumb, that the torque is pointed into the screen. So there's the torque. Okay, now we're going to do the same thing for the right part of the sphere. So once again, R cross F. I'm taking out my right hand, doing the right hand rule. Once again, I'm getting that on this part, the torque is also pointed into the screen. So torque. So we can see that whereas the forces cancel, the torques add. So the overall torque, which I guess I'll draw up here, is pointed into the screen. So now I'm going to briefly describe something called Larmor Precession, named after some guy named Larmor. So once again, I will draw our spherical electron, and and it is spinning along this axis. And here actually I'm going to write the angular momentum L. See, if it's spinning along this axis, then the angular momentum is going to be pointing along the same direction it's spinning. And once again, we have the magnetic field pointing off this way. And we calculated that the torque is pointed into the screen. Okay, so that's what we just had from last time. So the question I now ask is, what is going to happen to the angular momentum given that we have this torque? So remember that torque is equal to the derivative of angular momentum with respect to time. And because this torque is pointing at a right angle to the angular momentum, this angular momentum vector is going to travel in a circle, because that's what happens when the time derivative of a vector is always perpendicular to the vector. So here I'm going to try to draw the circle. It's kind of hard to draw, but all right, so this is the circle that the angular momentum vector L is going to travel in. And this is called precession. That's what precession is, when this angular momentum vector travels in this circle. So note that the axis of rotation of this precession is the magnetic field vector. So Larmor precession is just that when you have a spinning electric charge placed in an external magnetic field, the angular momentum due to the spinning is going to precess around the magnetic field vector. That's Larmor precession. So that's really my main point for this part of the video, that if you place a spinning particle in an external magnetic field, that the direction along which it's spinning will precess in a circle around the magnetic field. But actually, I want to take this opportunity to just mention that this is not the full story. So, not the full story. And maybe some of you could have already guessed that and can see why that is. So here's the problem. At the very beginning of this video, I said that the direction along which the electron was spinning was pointed straight up, right? I drew this vector omega sub spin pointing straight up. But if the electron is also precessing, right, then not only will the electron be rotating along the spin axis, but it will also be rotating along this axis of precession. So here I am now drawing omega sub precession. So the total direction along which the electron is rotating is this direction, which I'll call omega subtotal, where omega total equals omega spin plus omega precession. This makes the full behavior of the electron a lot more complicated. And what it will do is it will introduce a bit of wobbling. That's not the technical term, but that's essentially what it does. However, if the rate at which the electron is spinning, so if omega sub spin is much bigger than omega sub precession, right, then the amount of wobbling will be very small. And basically, Larmor precession will just be the full story. So, right, so if the rate at which the electron is spinning is, let's say, very fast, and it's very slowly precessing along the magnetic field vector, then the angular momentum vector basically points along the direction in which it's spinning, and the torque basically points at a right angle, and that's all there is to it. Now, so far, we've only been talking about classical physics, right? This has been a purely classical analysis. But it turns out that the quantum behavior of the spinning electron is actually simpler. So I guess I'll just write that here. Quantum behavior is simpler. And the reason that it's simpler is because there's none of this wobbling going on, right? So in other words, we have Larmor precession, which is just that the angular momentum vector goes around in a circle. And on top of that, we have wobbling. But in the quantum case, there is none of this wobbling. And that's basically because, don't tell anyone I said this, but you can sort of think of it as in the quantum case, the rate at which it's spinning, you can sort of think of it as it being infinite. Okay, don't tell anyone I said this because that might be embarrassing for my future career prospects. But it's just sort of one way, it's an imprecise way to think about it. That in a quantum case, you can think of the electron as spinning infinitely fast, so there is no angular momentum due to the precession of the electron. If you think that's a dumb way to think about it, don't worry about it. But if you think it's helpful, maybe keep it in the back of your mind. All right, now I want to get a little bit more quantitative and talk about the formula for torque. So let me just draw my axes. So here we have the x, y, and z axes. And my setup's going to be a little bit different from last time. Instead of thinking about the electron as a charged spinning sphere, I'm going to think about it as a square wire with a current circulating around the wire. So here's my square current of wire, which is in the xy plane. And there's some external magnetic field, which has the components Bx, By, and Bz. And on this wire, the square wire, we have a total charge of Q, which is circulating around the wire with some velocity, which I will call v. So v is the velocity at which this total charge Q is circulating around the wire. And I should say what the length of this wire is. So here I've drawn it as a square, and the length of each side I'm going to call L. I'm going to call the length L. Okay. So the next thing I want to calculate is the current going around this wire. So what is the current? Well, if I make this little square surface, right? Here I have this little square surface that the wire is passing through. The current, which I will call I, is equal to the amount of charge that passes through this square surface per unit time. Now, that is just equal to the total charge, Q, divided by how long it takes one little bit of the charge to make a full loop around the wire. So that's just Q over 4L over v. Okay, so 4L over v is just the amount of time it takes one little bit of the charge to make a full loop, because the total length of the wire is 4L, because L is the length of each side, right? And the total length is L plus L plus L plus L, and v is the velocity at which it goes around. So actually, just for kicks, I will write this again as QV over 4L. Okay, that's the current. Okay, the next thing I'm going to do is redraw our square wire, and I am going to write what the velocity is along each of these four parts of the wire. So along this part of the wire right here, the velocity is equal to the vector 0, v, 0, where it's going along the y direction, right? So that's the y component is v. Then along this part, I have that v equals negative v, 0, 0. Along this top part, I have that v equals 0, negative v, 0. Along this part, I have that v equals v, 0, 0. Okay, so the next thing I'm going to do is write what the average position vector of each segment of the wire is. So here's what I mean by that. So if I say that the center of the wire is this point, right, that's the origin, then this length right here is L over 2. And the average position of this segment of the wire is R equals L over 2, 0, 0. Right? So, in other words, that's this position right here. Now, for this segment of the wire, we have that R equals 0, L over 2, 0. For this segment of the wire, we have that R equals negative L over 2, 0, 0. And then for this segment of the wire, we have that R equals 0, negative L over 2, 0. Now, the next thing to note is that the charge on each segment of wire is just big Q over 4. So here I'm writing little q for just the amount of charge on each segment of wire, and that's big Q over 4, right? So I'll just write it on each segment. So little q equals big Q over 4, little q equals big Q over 4, and little q equals big Q over 4. Okay, great. Now I finally set up all of the relevant information for calculating the torque on this wire in this external magnetic field. So the force, as you remember from the Lorentz force law, is just equal to Q V cross B. And once you know what the force is, you can calculate the torque. And the torque is just R cross F. So there's now enough information on the screen to go around calculating the force on each of these 4 segments of wire and the torque on each of these 4 segments of wire. And only the average position is important for when you calculate the torque, because the contribution from this part and this part cancel out except for just the average position of the two. So I'm not going to actually go around in this video and calculate the force and torque in each of the 4 parts. I already did it before starting this video. I'm just going to write the final result just to save some time. But if you yourself want to do the morally good thing and check this for yourself, I have included enough information on the screen for you to just take out a piece of paper and do it. Just look up the formula for cross product, because unless you remember it. But it's just basically now you just have to do out all the cross products. But I'm just going to write the final answer. So after doing all those cross products and adding them up, we find that the total torque, so total torque is equal to, okay, let's see, we got Q L V over 4, just 4. I'll draw it in the center, times the vector negative by and bx. Okay, so the first thing to notice is that this prefactor QLV over 4, that is just equal to the current I times L squared. So this whole thing is just I times L squared, right? See, that's I. If you just multiply it by L squared, you get this thing. But L squared can be written in a different way, because L squared is just the area of this square. Right? The area is just equal to L squared. So instead of writing L squared, I'm going to write A, where A is the area of the square and A is L squared. So I'm going to write it now as equals IA times the vector negative by bx. Okay. Now, and I know we're going through a lot of steps here and just, rewriting stuff in a different way, but we can rewrite this as a new vector mu cross b, where this new vector mu is called the magnetic dipole moment. So sometimes just called the magnetic moment. The full name is the magnetic dipole moment. And it is equal to the vector with components 0, 0, and I times A. Now there's one last way, Now there's one last way we can write this vector mu in a different way, and that is as I times the normal surface vector A. So this surface vector A is just it's a vector with the magnitude of A pointing normal to the area of the square that the wire makes. So in other words, mu, this magnetic dipole moment, is just a vector, and it's pointing upwards, right? It's equal to I times A. And it should be thought of like, it should be thought of as the axis around which the current is flowing, right? Or to go harken back to the electron language, if you think of this whole thing as some sort of model for an electron, mu is the direction along which the electron is spinning. Or maybe opposite the direction. Anyway, you get the idea. The reason I said that is because the charge of the electron is negative, so it actually might be the direction negative along which the electron is spinning, but it doesn't really matter. You get the general idea. Okay, now I'm going to clear some of this up and rewrite the main result. So, if you have this square loop of current with a magnetic moment of I times A, where I is the current, and you just have this arbitrary external magnetic field B, then the total torque is just equal to mu cross B. This is the main result I wanted to show. Now, one of the really cool things about this equation, that the torque is equal to mu cross B, where mu is equal to I times A, is that this equation is actually true for any arbitrary shape of wire, not just a square. So let me quickly outline the argument for why that should be true. So say you have your wire in any old funky shape. Now you can take this shape and break it up into a grid of little squares. So here we have a grid of squares. And if you have a current of I, going around this wire, say that in every little square, you also have a current of I going around each individual little square. Now, the thing is that the current from this loop coming up this way will cancel out the current from this loop right next to it going this way, right? So there'll actually be zero current total in this little segment, and actually in this little segment, and every segment in the interior of this shape. However, what won't cancel out is the current traveling along the outside part of the wire, right? So the inside parts I'll cancel out, but the outside parts don't cancel out. So all these little squares will just add up to have the same exact current as the original loop. Now, meanwhile, the areas of each of these tiny little squares add up, right? So if you just sum all the areas together, right, you just get the area, of this whole shape. And the normal area vector, right, A, will just be the sum of all these little squares. And those all add up to some total magnetic moment mu. Meanwhile, all the torques from all of these little squares will also add up. So just given this sort of quick sketch of an argument I've given here, you can see that showing that this equation is true for a square also shows that it's true for any arbitrary shape of wire. And in particular, it's true for a circular shape of wire. So the next thing I want to do is to figure out the expression for the energy of a current in a magnetic field. Okay, so here is our setup. Here we have our same old square wire edge on. So we're seeing the same old square wire from the side. And throughout space, we have a constant magnetic field B. This side length right here is L over 2 because the full side length is L. And the angle that the wire makes with the magnetic field is an angle theta. And we have a total charge going around the wire in a current. So the total charge is Q. And it travels with some velocity v. So up this side of the wire, v is pointed like that. And then in this segment right here that's pointed into the screen, v is going like that. And then at this segment here coming out of the screen, v is pointed out like that. Okay, so that's the setup. Now what are the forces on the different segments of the wire? Well, remember that the expression for force is that force equals Q V cross B. And on each segment of the wire, the charge is big Q over 4. So let's start by looking at the force on the segment of wire that's pointed into the screen, right here. So let's do the right-hand rule to figure out the direction of V cross B. So I'm currently doing the right-hand rule, and I'm figuring out that V cross B points this way. And actually, just for this example, let's say that the total charge Q is greater than 0. So force points in the same direction as V cross B. So okay, the force here is pointed in this direction. It's pointed horizontally like this. And it's going to be equal to big Q over 4 V times B. Oh, actually, maybe I shouldn't write that vector there if I'm just dealing with the scalar quantity. Okay, so that's the force pointing this way. Now what about at this segment of wire over here coming out of the screen? Well, here doing the right-hand rule, V cross B, okay, let's see, is going to point in this direction. And the magnitude of the force is going to be equal to the magnitude of the force here. So once again, force is equal to Q over 4 VB. And what about this segment of wire going up like this? Well, here, let's see, V cross B is going to point out of the screen, like that. And for the segment of wire on the other side that we can't see, the force is going to point in the other direction. So this component of force is pointing normally to the length of the wire. But if we're assuming that the wire is going to be rigid, then this force doesn't matter, and it just cancels out with the force on the other side. So we don't have to worry about this force. We only have to worry about this force and this force. So note that this force here is always pointing horizontally, and it doesn't actually depend on whatever this angle theta is. So let me just write that. So force is always horizontal, and it doesn't depend on theta. Okay, so that's what the forces are. So actually, I want to try doing something now. I want to take all of this that we have right here, and I want to minimize it. So that looks pretty good. So I'm just going to tuck this away in the corner for right now. Okay. So now I'm going to redraw the setup. So here we have the magnetic field B, and we have the wire Yeah. And say that the wire makes some angle, which I'll now call theta sub 1 with the B field. And imagine taking this wire and through some process, doesn't really matter how, rotating the wire. So instead of making an angle of theta sub 1, it makes a different angle of theta sub 2. So now I am finally ready to pose the question I've been meaning to ask for a while. So question: what is the work done by the magnetic field B as the angle is changed from theta sub 1 to theta sub 2? So to answer this question, we have to remember that work is equal to force times delta x, where this is assuming that the force is constant and pointing along the direction of delta x. So, okay, so what's delta x here? Well, we only have a force acting on this part of the wire and this part of the wire, right? And the force is constant and horizontal. So delta x is going to be this distance right here, and also this distance right here. So actually, let me clean this up a little. Okay, so here we have delta x here, and the same thing, over here. So actually, because there are two sides to the wire, right, here and here, where we're thinking about the force acting on it, we actually want 2 F times delta x. So, okay, so what is delta x? Well, delta x is equal to, now remember that this side length here is L over 2. So delta x is equal to L over 2, and then this side length here is cosine of theta 1 times L over 2. And likewise for this length right here being cosine of theta 2. So okay, so delta x equals L over 2 times cosine of theta 2 minus cosine of theta 1. Okay, let's actually move some more stuff around now. I'm really moving a lot of stuff around. What can I say? Okay, so let's move this all the way down here, and let's move this thing up here. Okay. Okay, so let's recap what we're trying to do. We're trying to figure out the work that the magnetic field does in the wire when the angle is changed from theta sub 1 to theta sub 2. Now we know that it's equal to 2f delta x, where delta x is this thing we just solved for, and f is this quantity over here. So we can just plug in f and delta x to figure out that the work is equal to 2 times q over 4 v b times L over 2, I'll just copy this, cosine of theta sub 2 minus cosine of theta sub 1. And actually, you can get rid of this now. And this simplifies to be Q over 4 V B L times cosine of theta sub 2 minus cosine of theta sub 1. Now, once again, I want to express this whole thing in terms of the current I. So, from before, we figured out that I equals Q V over 4L, right? That's the current going around the wire. And also remember that A, the area of the square, equals L squared. So we have that, once again, I times A equals Q V L over 4. So, okay, actually let me just even get rid of this. So I times A equals, I times A equals QVL over 4. But note that QVL over 4 is basically what we have here. I mean, there's this extra B. But we can rewrite this whole thing here as I times A times B times, once again, cosine of theta 2 minus cosine of theta 1. And I'll even get rid of IA down here. Now next, remember that the magnetic moment vector mu is equal to I times A. So this expression right here can be rewritten as mu dot the B field in position 2. So by this notation here, like subposition 2, all I mean is that when the wire has an angle of theta sub 2, that's all I mean by that. And then minus mu dot B when the wire is in position 1. Okay, and I'll get rid of this thing right here. Okay, we finally did it. We finally figured out the expression for the work that the magnetic field does when the angle of the wire is changed from theta 1 to theta 2. This is our expression. So now that we've figured this out, we can now address our original question of what is the energy of this current in the external magnetic field. So in order to figure out what the energy is, remember that the work done by the magnetic field is equal to negative times the change in the potential energy of the configuration. So okay, why is this equation true? This is just true because of the conservation of energy. So the work is just equal to the kinetic energy added to the wire by the magnetic field. And negative delta U is just the potential energy lost by the change in the angle of the wire. So, okay, well, what did I write here? What is this, first of all, what is this kinetic energy I'm talking about? What kinetic energy was added to the wire? Well, just think about what's really going on in this situation, right? We have this wire which makes an angle with the magnetic field, and we have this constant force which is always pointed in the same direction and has the same magnitude no matter what theta is. So if you just look at the setup, right, it looks exactly the same as the setup for a pendulum, right? The pendulum has some angle with the vertical, and there's some constant gravitational force acting on the pendulum, right? And as a result, it will swing back and forth. Likewise, this wire will just swing back and forth like a pendulum. The only difference is here, I've drawn the force to be horizontal instead of vertical, but whatever. So by kinetic energy added to the wire by the magnetic field, I just mean the kinetic energy that comes from the fact that when the wire is moving back and forth, the different parts of the wire have some velocity, and that has some kinetic energy. Now, you might be saying, well, wait a second. Earlier, when we had a charged spinning sphere placed in an external magnetic field, which had a magnetic moment vector mu, this magnetic moment vector did not swing back and forth like a pendulum, right? So here, this would be our magnetic moment vector in this diagram, right? Instead, it precessed around B, right? So why is it that in the case of the charged spinning sphere, the magnetic moment vector mu precessed around B, but in the case of the wire, the magnetic moment vector swings back and forth like a pendulum, right? So it swings like that. And the answer is that in the case of the charged spinning sphere, the sphere itself has some mass. So when this mass rotates, it has some angular momentum. And ultimately, it's due to this angular momentum that the sphere will precess, right? However, in the case of the wire, we usually think of wires as having these tiny little electrons moving down the wire, and it's these tiny electrons which carry the charge and the current. And the thing is that because the electrons have a negligible mass, there is essentially no angular momentum coming from the fact that these electrons are circulating around the wire, right? And because there's no appreciable angular momentum associated with this current, the wire won't precess. It'll just swing back and forth like a pendulum. In other words, you can essentially think of it as a difference between a gyroscope, right? So here we have a gyroscope mounted to this pivot, and it's spinning around. It's this wheel spinning around in a gravitational field. And we can think about it as the difference between a gyroscope and a pendulum, right? So a gyroscope will precess around the vertical axis, right? Whereas a pendulum will just swing back and forth. So the difference between a gyroscope and a pendulum is the exact same thing as the difference between the charged spinning sphere and the wire. All right. So, okay. Nothing too crazy. All right, so now that we have some appreciation for the physics of what's going on, we are now finally ready to write the expression for the energy of a current in a magnetic field. So, from these two equations right here, we can immediately see that the potential energy U is equal to minus the magnetic moment vector mu dot the magnetic field B. And this is the expression for the energy of any sort of current in an external magnetic field. So this expression that we've derived here is a very important and very general expression. Even though we've only shown that it's true for a square current, it's actually true for any shape of current. So, once again, we can use the same exact logic as before. Say that you had some funky shaped current. You could break it up into a grid of little squares and yada, yada, yada through reasoning similar to, what we went through before. This expression should be true for the funky shape of current as well as, for the square shape. And in particular, it's also true for current going in a circle, which is very important. So, okay, we've just derived this great expression for the energy of a wire in an external magnetic field. But what we really want is the energy of a charged spinning sphere in an external magnetic field, because the charged spinning sphere is our toy model of the electron. So let's see if we can use what we know about the wire to figure out a similar expression for the charged spinning sphere. So I'm going to tuck this away in the corner, and then I'm just going to modify the title a bit to be charged spinning sphere. Okay, it's a little janky, but it's okay. So before we get to the sphere, let's start with a charged spinning ring. So here I have a spinning ring of charge with a mass of m, and let's say this thing has a charge of q, and it has some angular momentum L, and the ring itself has a radius of r, and let's say that the rim is spinning with a, whoops, slightly the wrong color. Let's say the rim is spinning with a velocity of v. So let's write out a few of these quantities here. So L is equal to m v r, right? That's just the angular momentum L. And what about I? So because this charge ring is spinning, it's going to have some current I. And that's just going to be equal to the charge which passes through a surface per unit time. And that's just equal to the total charge Q divided by the period of the ring. And what's the period of the ring? It's just, let's think, it's 2 pi r, which is the perimeter of the ring, divided by v, right? That's the time it takes for the ring to rotate once. And actually, let's write that a little bit differently. Let's put the v up top. So, okay, that's the, clean up a little. That's the current I. Now, the next thing I'll write is the area of this ring, which is just pi r squared. So now that we have the current I and the area A, let's write what mu is, where mu is the magnetic moment. Now this is equal to I times A, which is equal to Q V R over 2. Now, just messing around a little bit, we can rewrite this as Q over 2m times mvr. And mvr is just the same thing as L. So we can rewrite this as Q over 2m times L. And because mu here will point in the same direction as the vector L, we should actually write this as the vector expression. The vector mu is equal to Q over 2m times the vector L. So this is the magnetic moment for this spinning ring of charge. Okay, very cool. So let me clear some of this scratch work here and move this over here. So, okay, from this expression for U here, we can see that for the spinning ring of charge, U is equal to negative and then Q over 2m L dot the magnetic field, the external magnetic field B. Now, the good thing about this expression we've derived here is that it turns out that it is also true for a spinning sphere of charge. So, also true for spinning sphere of charge. And why is that? Well, a spinning sphere can just be thought of as an infinite number of spinning rings, right? So you can imagine having a bunch of spinning rings that when you put them together, they comprise a spinning sphere, right? Now, look at this prefactor Q over 2m, or really just Q over m. That's equal to the charge density of the ring divided by, well, 2 times the mass density. But don't worry about the 2. So if you assume that this spinning sphere has a constant charge density per mass density, then this prefactor, Q over 2m, will be the same for each of these infinite number of spinning rings that comprise the spinning sphere. Therefore, you can just add up all of the angular momenta from each spinning ring. And because the angular momenta of all of the rings adds up, and the energy from all of the rings adds up, then we can immediately see that this whole expression, as promised, will be true for a spinning sphere of constant charge density per mass density, straight from the fact that it's true for the spinning ring. And with that, we conclude the classical physics part of this video, and we'll now go on to talk about quantum mechanics. This expression that we've derived for energy is going to come back, though, so keep this in mind. You could make the argument that there's not really any point to talking about the classical physics of a charged spinning sphere, because electrons are not actually charged spinning spheres, right? There's no actual rotation in a quantum spin. It's just a picture that we have in our head. It's sort of, I saw it summed up in this meme, which I have right here. Okay, so let's look at this meme I saw. Okay. Electron spin explained. Imagine a ball that's rotating, except it's not a ball and it's not rotating. So this is the explanation a lot of people give for quantum spin. And it's sort of funny, but I don't really know how else to talk about it. The thing is that there are a lot of genuinely important lessons to learn in the classical physics case and some equations that carry over. But you also can't take the charged spinning balls too seriously because, well, electrons aren't actually charged spinning balls. Okay. So now we are going to finally talk about quantum time evolution. I.e., the Schrödinger equation. Okay. So a quantum spin state, which we usually write like this, is a vector comprised of two complex numbers, which I'm going to call C1 and C2. So C1 and C2 are both complex numbers. They're an element of the set C. This is the set of complex numbers. Okay, so now we want to talk about how these spin states evolve in time. So now the spin state is going to be a function of time. And each of the complex numbers that comprise it are both functions of time. Now, usually in physics, when we have an equation that tells us how something changes in time, we phrase this equation in terms of the time derivative of what it is we're interested in. So we want to know what the time derivative of this state is. So d dt of this state. And by the time derivative of this quantum spin state vector, I just mean the time derivative of each of these components separately, right? It's nothing fancy. So the time derivative of this state is going to be given by an equation called Schrödinger's equation. It's going to tell us how our state evolves in time. So I am now going to write Schrödinger's equation, right? SE, that stands for Schrödinger's equation. Okay. It is I times h bar, where this is a Planck's reduced constant, times d dt of our quantum spin state psi of t, right, equals h, and I'll talk more about h in a second, times the quantum spin state psi of t. So here h is a 2 by 2 matrix, which is called the Hamiltonian, named after some guy named Hamilton. So once I tell you what this 2 by 2 matrix H is, I will have finished telling you what the Schrödinger equation is. But instead of just telling you what H is, I want us to look at this equation and see if we can sort of make an educated guess ourselves for what H is. So let's start by looking at the left part of the equation, right? Here we have this I here, and that's pretty interesting, and there's a good reason for that to be there, but we won't really talk about that right now. And then we have here Planck's reduced constant. Now, Planck's reduced constant h bar is approximately equal to 1.054 times 10 to the negative 34, right, so it's very small, joules times seconds. Right, so that's just what Planck's reduced constant is. It's a physical constant. So look at the units of Planck's reduced constant. That's what I want you to look at. Joules times seconds. So the dimensions of h bar, and here these brackets just mean the dimensions, of h bar is energy times time. And that's just because a joule is a unit of energy. Okay. So actually I need some of this space, so I gotta clear some of this stuff up. So move this up here, and I'll move this up here too, and I'll get rid of this. Okay. So whenever you have an equation, like Schrödinger's equation here, the dimensions of both sides of the equation have to be the same in order for the equation to even make sense. So we can figure out what the dimensions of the Hamiltonian h have to be by figuring out what the dimensions of the left side of the equation are. So, okay, what are the dimensions of this left side of the equation? Well, right off the bat, we have this weird thing here. We have the imaginary number I. So what are the units of I? Well, if you think about it, you can do stuff to I like, adding it to 1 or, adding it to 3 and stuff like that. And because numbers like 1 and 3 don't have any units, because you can add I to numbers without units, it makes sense to say that I itself doesn't have any units. So I is unitless. It's like 1. Now next, the dimensions of h bar, as we already know, are energy times time. Next, what are the dimensions of d dt of psi of t? Well, we know that psi of t is just a vector with two complex numbers. But as we already discussed, complex numbers don't have any units. So what we're basically doing here is we're differentiating unitless numbers with respect to time. And if you think about it, d dt of, well, let's just say c1, right? Let's just look at the top component. So d dt of c1 is equal to, let's say the limit as delta t goes to 0 of c1 of t plus delta t minus c1 of t over delta t, right? So the numerator of this fraction, c1 of t plus delta t minus c1 of t, this is just a unitless number because c1 of t plus delta t is unitless and c1 of t is unitless. So this top part is unitless. Now the bottom part, delta t, this has units of time, right? It's an infinitesimal time, but has units of time nonetheless. So getting rid of all that. Okay. The dimensions of this thing right here, the dimensions of this are just 1 over time. Now, let's look at the right part of the right half of the equation now. So, as discussed, this thing has no units, right? Psi of t has no units. It's dimensionless. So, therefore, the dimensions of h have to be energy times time divided by time. In other words, the dimensions of h have to be energy. So now that we can see that h has units of energy, we're going to make a guess. Here's our guess. H is somehow a quantum version of U, where U is the classical potential energy of a spinning charge in a magnetic field, right? So we derived that U, and we derived this classically, but we're just going to, we're just making an educated guess, right? This isn't rigorous. So our classical equation was that U equals negative Q over 2m times the angular momentum L dot the external magnetic field B. So we want to somehow take this classical equation and somehow make it work quantum mechanically, right? This isn't rigorous. This is just, it's just a reasonable guess. Okay, so now we're going to construct our guess for what H is. Actually, I always need some more space. Okay, so we are now going to construct our guess for what H is. Okay, so right off the bat, we got this prefactor, negative Q over 2m. Now, the charge of an electron Q is equal to negative E. We like to have physical constants be positive. So because an electron is negatively charged, we say its charge is negative E. So the negative here and here cancel out, and we're just left with E. And then over 2m. Well, in quantum mechanics, electrons still have mass, so that part doesn't change. Here, m is just the mass of the electron, right? Okay, so now things get a little bit weirder. L. What is the angular momentum L of an electron in quantum mechanics? Well, it turns out that the angular momentum of an electron is h bar over 2. And it's kind of funny that h bar has the units of angular momentum, because here we saw that it had the units of energy times time. Now it turns out that the units of angular momentum actually can be written as energy times time. So let me actually show that quickly. So energy times time. Let's break this down. Now energy has the units of mass times velocity squared, right? And you can see that, for instance, from the equation that kinetic energy is equal to 1/2 mv squared, right? So this is the equation I always think about when I try to remember what the units of energy are. So we can break this down even further to be mass times distance squared over time squared, and then times time. And then here the times cancel out, so this can be rewritten as mass times, well, distance over time, and then times distance. Just rewrote it a little bit differently. And then note that mass times distance over time, those are the units of momentum, right? Mass times velocity. So this has the units of momentum times distance. And then from the classical equation, L equals position cross momentum, you can see that the units of angular momentum are just momentum times distance, which, as we can see, are the same as energy times time. So okay, h bar really does have the units of angular momentum, which is kind of funny given that it's appearing in these two quite different places. So that's h bar for you. It's a pretty interesting constant, right? It's funny that it appears here in the Schrödinger equation and then again as the angular momentum of an electron. So okay, what is L? Well, it should have h bar over 2 incorporated into it somehow. But we need L to be a vector, right? Because angular momentum is a vector. But what's more is that we need H to be a 2 by 2 matrix, right? Remember at the beginning of this I said that H was a 2 by 2 matrix? So how do we get H to be a 2 by 2 matrix while also getting L to be a vector, right? We had these two problems. Well, it turns out that we can kill two birds with one stone by making L a vector of matrices. And if you've seen my video on the block sphere, this should be pretty reasonable to you. But what are these matrices? Well, these are the three Pauli matrices, and I'll just write them out again just to remind you. So sigma sub x has entries 0, 1, 1, 0. Sigma sub y has entries 0, negative I, 0. And sigma sub z has entries 1, 0, 0, negative 1. Now, if it doesn't really make sense to you to have a vector of matrices, don't worry about it too much. It's really just sort of tongue-in-cheek notation. It doesn't really mean a whole lot, right? It's just sort of, if you want to talk about the angular momentum in quantum mechanics, this is the best way to do it. But it shouldn't let you worry you. Okay. So now what do we have here? We have L dot B. Now what is B, right? B is the magnetic field. Is just a vector with components Bx, By, and Bz. So when we see classically, we see L dot B, how are we going to translate this in our quantum case here? Well, just borrowing the notation for the dot product, it turns out that L dot B should just be h bar over 2 times B sub x sigma sub x plus B sub y times sigma sub y plus B sub z times sigma sub z. Right? This is the correct way to do L dot B, right? And if you notice, plugging this all into H, this, oh, sorry. This gives us our desired result of H being a 2 by 2 matrix, right? Because this is a 2 by 2 matrix, this is a 2 by 2 matrix, this is a 2 by 2 matrix. And if you just add up 2 by 2 matrices, well, the result is just overall a 2 by 2 matrix. So this has achieved our result of making H a quantum version of the energy of the electron and also being, at the same time, a 2 by 2 matrix. So it seems as though we're done. We've taken every term in U and put it into H. However, we are not yet done. And there is one final term called G, where G is something I've never told you about before, called the gyromagnetic ratio. And it's a unitless number which is approximately equal to 2. So there's no way we could have guessed, by the way, that this gyromagnetic ratio was going to be there. In a way, it sort of makes sense that this happened, right? I mean, all we did was we took this equation, which is true in classical mechanics, and tried to make it make sense in quantum mechanics. And we almost did it. We almost got the right answer, but we were off by approximately a factor of 2. It's sort of interesting that it almost worked. We were so close. So anyway, now that we know what the Hamiltonian H is, we now have completely explained what Schrödinger's equation is, right? So we now know, in principle, how states in quantum mechanics evolve in time. And in the next video, I'm going to talk about how to solve Schrödinger's equation. But right now, I want to talk more about the gyromagnetic ratio, right? Like, what's up with this thing? How should you think about this thing? So that's what the rest of the video is going to be. I just want to talk about this gyromagnetic ratio and say what its deal is, right? Because it's totally unexpected. So the G factor. A field trip to QFT. Okay. So, there are 4 main realms of physics, which I'm going to put in this chart here. So in this column here, we got slow stuff, and then in this column we got fast stuff. And then in this row here we got big stuff, and then in this row we got small stuff. So the realm of physics that deals with stuff that is both big and slow is Newtonian mechanics. You know, F equals ma and all that. The realm of physics that deals with stuff that is both big and fast is relativity. And by fast, I just mean stuff that's traveling at close to the speed of light, right? Like Newtonian mechanics only deals with stuff traveling much slower than light. Okay. Now, what realm of physics deals with stuff that is both small and slow? And by slow, I mean much slower than light. This is the realm of physics called quantum mechanics, often abbreviated QM. And then the realm of physics that deals with stuff that is both small and fast is called quantum field theory, often abbreviated QFT. Quantum mechanics describes small stuff like electrons when they aren't moving near the speed of light. And in this whole video series, I've only been talking about quantum mechanics. Now, even though I haven't gone into the motion of the electron, I've just been thinking of them as these stationary point particles and talking about their spin. In a future video, I'm going to talk a bit about how to deal with motion. And in quantum field theory, though, you can talk about electrons when they're moving near the speed of light. So here, quantum mechanics is the less deep theory, right? Whereas quantum field theory is the more deep theory, right? Now, quantum field theory, and more specifically the standard model of particle physics, is the deepest known theory that we currently have in physics, which describes elementary particles. Quantum field theory and Einstein's theory of general relativity together are the 2 deepest theories that modern physics has, but as of yet they cannot be mathematically reconciled. We would have to develop a theory of quantum gravity in order to do that, but as of now we have no idea what that theory is. Maybe it's string theory, maybe it's something else, but no theory, including string theory in its current form, is even a mathematically complete theory, let alone experimentally verified. So we would need a theory of quantum gravity, for instance, to talk about what happens in the singularity of black holes and stuff like that. The reason I'm telling you about quantum field theory is I want to make it clear that I am not giving you the deepest possible theory of electrons, which is quantum field theory. The reason I'm not doing that is because quantum field theory is a much more complicated subject than quantum mechanics. And in order to start learning quantum field theory, you have to already know quantum mechanics very well. Now, because of this, because I'm not assuming that you know anything about quantum field theory, I cannot give you a rigorous derivation of Schrödinger's equation, right? And that's because you can't derive stuff about a more deep theory from a less deep theory, right? So in this case, if all you know is classical mechanics, I can't derive stuff about quantum mechanics from classical mechanics. Now, if you knew quantum field theory, then I could actually derive Schrödinger's equation. But because you don't, I can only make motivations, right? You're not totally in the dark. You know, you can motivate stuff about the more deep theory from a less deep theory, but you can't make any rigorous derivations. Now, there's nothing wrong with this, right? I mean, in some sense, this is how science works. So people initially figured out Schrödinger's equation through a mixture of guessing and experimental evidence. And in that sense, you can think of Schrödinger's equation as sort of like F equals ma in Newtonian mechanics, right? So in Newtonian mechanics, F equals ma cannot be derived, right? It's a starting point. So, Newton didn't derive F equals ma. He postulated it based on, all the work Kepler had done on figuring out the orbits of the planets and all that, and then realized it applied to other situations. Right? But you can't derive F equals ma in Newtonian mechanics. You can choose an equivalent starting point, for instance, maybe the principle of least action, and then from there you could derive F equals ma, but then you couldn't derive the principle of least action, right? That would just be a different starting point. Now, if you do know a more deep theory than Newtonian mechanics, then you can derive F equals ma. So for example, if you know Einstein's theory of general relativity, then in a certain limit you can see how Einstein's theory of general relativity reproduces Newton's equation for the force of gravity, right? So in that sense, it's sort of like how if you know quantum field theory, you can derive Schrödinger's equation in quantum mechanics. Another way that Schrödinger's equation is similar to F equals ma is that F equals ma is what is known as an equation of motion. And this means that if you have some physical system with some particles and you know all of the particles' positions and velocities at some initial time, and you know all the forces between the particles, you can use F equals ma to figure out all the future positions and velocities of those particles and all of the past positions and velocities. Likewise, using Schrödinger's equation, if you know the quantum spin state of an electron at some given time, you can figure out what the quantum spin state will be at all future and all past times. Okay, but I've gone off on a bit of a tangent here because all I really want to do is tell you about the G factor. So initially, before people figured out that this factor of G was a little bit bigger than 2, they first thought that it was exactly equal to 2. And they figured this out, by doing experiments. And this was surprising to people because classically you expect G to be equal to 1. So people are like, well, wait a second, why is G equal to 2? And the first person to give a theoretical justification for why G was equal to 2 was Paul Dirac in 1928. And when he did this, he was only 25, so, it'll make you feel really bad. Actually, it makes me feel pretty bad that he was only 25 when he did this. So, so he published a paper in 1928 called The Quantum Theory of the Electron, in which he gave the correct wave equation describing the electron, which correctly takes special relativity into account. So you can sort of think about this factor of 2 as coming from correctly taking special relativity into account. However, I said that G is actually not exactly 2. It's a little bit bigger than 2. And the first person to ever provide a theoretical calculation for the value of G to more decimal places was a man named Julian Schwinger, who figured this out in 1947 when he was only 29 years old. And in order to explain why G isn't exactly 2, I have to say a few things about quantum field theory. Now, so far in this video, I have been talking about the magnetic field the same way you would talk about it in classical mechanics. Namely, the magnetic field is just a vector field with a different vector at each point in space. But in quantum field theory, the electromagnetic field is a much more complicated thing, and I can't really do it justice in this video. But basically, in quantum field theory, the electromagnetic field is made up of photons, which are themselves quantum particles. And I can't really explain too well what I mean by that when I say that the electromagnetic field is made up of photons. But basically just think of it as if there are more photons, somewhere, then the electromagnetic field is stronger there. Let's just say that. Anyway, one compelling picture people usually draw to talk about how electrons interact with the electromagnetic field is to draw these things called Feynman diagrams, where you have an electron emitting or absorbing a photon. Now, whether it's really fair to say that electrons emit or absorb photons is up to some debate, but let's just go with this for now. Anyway, these Feynman diagrams aren't just cool-looking pictures. They are actually indispensable calculational tools. So when you want to calculate certain quantities in quantum field theory, you can phrase your calculation in terms of Feynman diagrams and use something called the Feynman rules to change each diagram into some sort of complicated integral, and then once you do this integral, you then get your answer. So in order to calculate the G factor in which a lone electron interacts with the electromagnetic field, you want to draw all of the Feynman diagrams in which a single electron comes in and out, which is denoted like this, and a single photon comes out. So in this shaded circle here, we want to draw all the Feynman diagrams which have these three external legs. Now, I'm not going to tell you all the Feynman rules, but I will tell you one Feynman rule. So here is one Feynman rule. So for every two vertices, and by vertex I mean one of these interaction vertices where an electron interacts with a photon, multiply the number by this coupling constant called alpha. Now, alpha is equal to 1 over 4 pi epsilon naught times e squared over h bar c. Now, this 1 over 4 pi epsilon naught, this is the same factor as present in the Coulomb force, right? So if you remember, the Coulomb force is 1 over 4 pi epsilon naught times the charge of the two things over r squared, right? This is the same 1 over 4 pi epsilon naught. E squared is the charge of the electron squared, and h bar is Planck's reduced constant, and c is the speed of light. Now, interestingly, this whole constant here is actually unitless. It's a unitless number, and it is approximately equal to 0.007297, which is approximately equal to 1 over 137.036, which is approximately equal to 1 over 37, as people like to say. This is called the fine structure constant. That's the name of alpha. Now, you should think about the fine structure constant as providing a dimensionless measure of how strong the electromagnetic force is. So we can see that the fine structure constant is about 1 over 137, which is less than 1 over 100. So 1 over 100 is a pretty small number, so we can say that the electromagnetic force is pretty weak because 1 over 100 is a pretty small number. Now, this also means that because alpha is very small, the more and more vertices a Feynman diagram has, the less and less it matters. So let's draw some of these diagrams to see what they look like. So the easiest diagram you can draw is just this one. Nothing crazy going on here. Another diagram you could draw is the same thing, but with one extra photon added right there. And then, maybe you could draw one like this with 2 photons, and maybe you could draw one like this with 2 photons like that. You get the idea. Now, in the case of the G factor, this first diagram gives you the 2 that Dirac originally found. And then the second diagram ends up being alpha over pi. Now, as I said, there's this complicated integral you have to do and stuff, but that just reduces to pi. You can see, though, that it's going to have one factor of alpha in it, though, because it's got 2 extra interaction vertices from the first diagram. So if the first diagram has no powers of alpha, the second diagram has 1 power of alpha. And then all of these other diagrams, you can see they have 2 photons added or more. Those are going to be higher order terms in alpha, so order alpha squared. And you might be saying, well, wait a second, what about like this diagram and stuff with this photon added? Turns out that this diagram and the other one you could draw like this don't actually contribute to G, so those ones don't matter. So these are this is the important one at the 1 alpha order. Now, remember that because alpha is very small, right? It's less than 100, so that's a pretty small number, I'd say. These more complicated Feynman diagrams don't contribute that much to the G factor. They contribute less and less the more complicated the diagram is. And that's actually good, because it turns out that the more complicated a Feynman diagram is, the harder the integral becomes. So, and when you have 3 vertices, it's like really, really hard. It's better to just call it quits after the first one and say, you get the general idea. You can say that the next leading order corrections to the G factor come from the fact that the electron creates its own electromagnetic field, which it itself then feels. So in this picture, you can see that the electron emits a photon, which it later absorbs. So you could say that that is the electron feeling the effect of its own electromagnetic field. This diagram here, which gives you the alpha over pi, is essentially the diagram that Julian Schwinger calculated in 1947. Now, Julian Schwinger did not actually use Feynman diagrams. He was working during the birth of quantum field theory, when everyone had their own way of doing things. And Julian Schwinger and Richard Feynman were personal rivals, actually, who had a lot of respect for each other. And during the late 40s, they were each racing to derive the next result in quantum field theory before the next one could. The methods that Schwinger used were really, really complicated. And the fact that the whole calculation reduced to alpha over pi struck him as this really beautiful result. So while Julian Schwinger had to work really, really hard just to derive the first correction to the G factor, we now know it to many higher orders in alpha, and it has in fact been experimentally verified to 15 decimal places, if you can believe that. So let me actually write out what we know G to be so far, just because I think it's kind of fun to write these really precise numbers. Okay, it's not quite done. Okay, and there's some uncertainty in the last 2 digits. Now, for his contribution to physics, Julian Schwinger won the 1965 Nobel Prize in Physics, sharing it with Richard Feynman and another physicist named Shinichiro Tominaga. Now, you always get the impression that this alpha over pi was the result of his that he was most proud of. And in fact, he put this alpha over pi, or I think maybe it's alpha over 2 pi, on his tombstone. So to this very day, if you go and visit Julian Schwinger's grave, you will see this thing right here. While making this video, I decided to visit Julian Schwinger's famous grave to see it for myself. He's buried in Mount Auburn Cemetery in Cambridge, Massachusetts, just a 30-minute walk from where I currently live. I went on a beautiful summer day and walked through a part of the city I don't normally see.
Where are we going, Noah?
We are going to see Julian Schwinger's grave.